Have you ever looked up at the night sky filled with countless stars and wondered where it all came from? How did this vast and intricate universe come to be? In the 20th century, a revolutionary idea emerged, the Big Bang Theory. Imagine the entire universe compressed into a tiny point smaller than an atom. This point, unimaginably hot and dense, contained the seeds of everything that would become the cosmos. Then, in a cosmic burst of energy and light, it happened. The Big Bang. The Big Bang Theory provides a framework for understanding the universe's journey from that initial moment to the vast cosmos we observe today. The Big Bang wasn't your typical explosion, with things flying apart into pre-existing space. Picture a loaf of raisin bread dough rising in the oven. As the dough expands, the raisins within it move further apart. The Big Bang was the initial expansion of this dough, carrying the galaxies along with it. This expansion wasn't a one-time event, it's still happening today. We observe distant galaxies moving away from us. The further away a galaxy is, the faster it appears to be receding. This observation suggests that the universe is constantly stretching and growing. But what caused this initial expansion? What was there before the Big Bang? These are some of the most profound questions in cosmology. One of the most remarkable aspects of the Big Bang Theory is that it allows us to look back in time. Light, traveling at the fastest speed possible, takes time to reach us from distant objects. When we look at a star that's 100 light-years away, we're seeing it as it was 100 years ago. By observing incredibly distant galaxies and quasars, astronomers are effectively peering back into the universe's history. These observations have provided a wealth of information, confirming key predictions of the Big Bang Theory. We've learned that the universe has gone through distinct phases, from the hot, dense soup of elementary particles to the formation of the first stars and galaxies. The Big Bang Theory helps us understand our place within the universe. We live on a small planet orbiting an average star, in a galaxy among billions of others, in a universe that's constantly expanding. We are a product of the Big Bang, formed from the same stardust that makes up everything we see around us. This realization inspires awe and wonder, but it also underscores our responsibility to understand and protect our pale blue dot. The Big Bang Theory connects us to the cosmos, a story that continues to unfold with every new discovery. Before the Big Bang Theory, the prevailing view of the universe was one of stasis and permanence. The universe was thought to be static, unchanging, and infinite in extent. This view was challenged by observations of spiral nebulae, faint, fuzzy patches of light observed through telescopes. In the early 20th century, astronomers debated whether these nebulae were part of our own Milky Way galaxy or distant island universes. The answer to this question would have profound implications for our understanding of the universe's scale and structure. In the 1920s, Edwin Hubble made a groundbreaking discovery that revolutionized our understanding of the universe. Using the Hooker telescope, Hubble measured the distances to several spiral nebulae, confirming they were distant galaxies. Hubble's most significant finding came when he combined his distance measurements with redshift data. He noticed a striking correlation. The farther away a galaxy was, the faster it appeared to be moving away from us. This relationship, now known as Hubble's law, provided the first direct evidence that the universe was expanding. Hubble's discovery shattered the long-held belief in a static universe and opened up a Pandora's box of questions. If the universe was expanding, what did that imply about its past? Was there a beginning to this expansion? Hubble's observations of an expanding universe sparked the great debate in astronomy. On one side were proponents of a dynamic, evolving universe, while on the other were those who clung to the traditional view of a static, eternal cosmos. Harlow Shapley, a renowned astronomer, remained skeptical of Hubble's findings. However, the evidence for an expanding universe continued to mount, with more distant galaxies exhibiting redshift consistent with Hubble's law. In 1927, Georges Lemaitre proposed that the universe originated from a single point, the primeval atom, and had been expanding ever since. Lemaitre's idea, initially met with skepticism, was a visionary leap of imagination. He envisioned the universe's history in reverse, tracing its expansion backward to a point of unimaginable density and temperature. He called this initial state the primeval atom or the cosmic egg. According to Lemaitre's theory, the universe began with the explosion of this cosmic egg, an event we now call the Big Bang. As the universe expanded and cooled, the primeval atom's energy condensed into matter, forming the first particles, atoms, stars, and galaxies. Despite the elegance of Lemaitre's theory, it faced resistance from some quarters. The idea of a universe with a beginning seemed to some to be too close to religious dogma. The debate over the Big Bang theory raged on for several decades. However, the tide began to turn decisively in favor of the Big Bang in the 1960s, with a groundbreaking discovery, the cosmic microwave background radiation, or CMB. In 1964, Arno Penzias and Robert Wilson detected a faint, persistent hum of microwave radiation that seemed to come from every direction in the sky. This hum, initially dismissed as noise, turned out to be a relic of the Big Bang itself. The CMB is a faint afterglow of the Big Bang, a symphony of light that has been traveling through the universe for billions of years. The discovery of the CMB provided compelling evidence for the Big Bang theory. It confirmed that the early universe was indeed extremely hot and dense, as predicted by Lemaitre's model. Imagine all the matter and energy in the universe squeezed into an infinitesimally small point, a point of infinite density and temperature. This is the singularity, the starting point of the Big Bang. At the singularity, the laws of physics as we know them break down, time and space as we perceive them cease to exist. Despite its enigmatic nature, the singularity is a crucial concept in cosmology. Some physicists believe that quantum gravity might hold the key to unlocking the secrets of the singularity. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion known as cosmic inflation. Imagine a grain of sand suddenly ballooning to the size of the observable universe. That's the scale of cosmic inflation. During this brief but crucial period, the universe expanded at a rate faster than the speed of light. Cosmic inflation solves several cosmological puzzles, such as the horizon problem and the flatness problem. Think of it like blowing up a balloon. As you inflate it, the surface becomes smoother and flatter. The expansion of the universe didn't stop after cosmic inflation. It's been happening ever since, albeit at a less dramatic pace. We observe distant galaxies moving away from us. Space itself is stretching, carrying the galaxies along with it. The expansion of the universe has profound implications for our understanding of time and space. It suggests that the universe was smaller and denser in the past, leading us back to the singularity. As the universe expanded and cooled after the Big Bang, energy began to condense into matter. This primordial soup of elementary particles, quarks, leptons, and bosons formed the building blocks of everything we see around us. In the first few minutes after the Big Bang, the universe was like a giant particle collider, with particles constantly colliding and interacting. As temperatures cooled, quarks combined to form protons and neutrons, the constituents of atomic nuclei. Over hundreds of thousands of years, electrons began to settle into orbit, forming the first atoms, marking a crucial transition in the universe's history. Section 5, Echoes of Creation, the Cosmic Microwave Background Radiation. About 380,000 years after the Big Bang, something remarkable happened that would forever change the universe and provide us with a glimpse into its infancy. The universe, having cooled sufficiently, allowed for the formation of neutral hydrogen atoms. This event, known as recombination, released a flood of photons that had been previously trapped by the sea of free electrons. These photons, messengers from the early universe, have been traveling through the cosmos ever since, their wavelength stretched by the expansion of space. Today we observe them as the cosmic microwave background radiation, a faint afterglow of the Big Bang that permeates all of space. The discovery of the CMB in 1964 provided the most compelling evidence yet for the Big Bang theory. It confirmed that the early universe was indeed a hot, dense soup of particles, as predicted by the theory. The CMB's uniformity also supports the idea of cosmic inflation, which smoothed out any initial irregularities in the universe's density. Section 1. Echoes in the Static, Unveiling the Cosmic Whisper. Imagine you're listening to an old vinyl record and through the hiss and crackle, you hear a faint melody, a whisper from the past. That's what it's like for cosmologists studying the cosmic microwave background radiation, the faint afterglow of the Big Bang. It's a signal from a time when the universe was young, hot, and dense, a time long before stars and galaxies even existed. In the 1960s, Arno Penzias and Robert Wilson, two physicists at Bell Telephone Laboratories, stumbled upon this cosmic whisper while testing a sensitive microwave antenna. They were puzzled by a persistent hum, a faint signal that seemed to come from every direction in the sky. At first they thought it might be interference from pigeons roosting in the antenna, but even after evicting the birds, the signal persisted. Unbeknownst to them, physicists at nearby Princeton University had been working on theoretical predictions for the afterglow of the Big Bang, a faint bath of radiation that should permeate the universe. When Penzias and Wilson heard about this prediction, they realized they had stumbled upon something truly extraordinary, direct evidence for the Big Bang. Section 2. Redshift Rendezvous. Galaxies on the run. Picture yourself standing on a sidewalk as a police car speeds past, its siren wailing. As the car moves away from you, the pitch of the siren seems to decrease. This phenomenon, known as the Doppler effect, also occurs with light waves. When an object is moving away from us, the light it emits is stretched, shifting towards the red end of the spectrum. This is known as redshift. In the 1920s, Edwin Hubble made a groundbreaking discovery. He observed that the light from distant galaxies was redshifted, indicating that they were moving away from us. Moreover, he found that the farther away a galaxy was, the faster it appeared to be receding. This relationship, now known as Hubble's law, provided the first direct evidence that the universe was expanding. Imagine you're baking a loaf of raisin bread. As the dough rises, the raisins embedded within it move farther apart. Similarly, as the universe expands, the galaxies within it are carried away from each other. Hubble's observations, combined with the discovery of the CMB, provided compelling evidence for an expanding universe, a key prediction of the Big Bang theory. In the cauldron of the early universe, just minutes after the Big Bang, the stage was set for the formation of the first elements. The extreme temperatures and densities allowed protons and neutrons to fuse together in a process called Big Bang nucleosynthesis. This primordial nuclear furnace produced a universe with a specific abundance of light elements, primarily hydrogen and helium, along with trace amounts of lithium and beryllium. The predicted abundances of these elements, based on the Big Bang theory, have been meticulously calculated and compared to observations of the oldest stars and gas clouds in the universe. And guess what? They match remarkably well. This agreement between theory and observation provides strong evidence that our understanding of the early universe, as described by the Big Bang theory, is on the right track. Think of it like this. Imagine you're a detective investigating a crime scene. You find fingerprints at the scene and compare them to those of a suspect. If they match, it's strong evidence that the suspect was present at the scene. Similarly, the matching abundances of light elements in the universe provide a fingerprint of the Big Bang, supporting the theory that it actually happened. One of the most remarkable aspects of astronomy is its ability to look back in time. Because light takes time to travel vast cosmic distances, when we observe distant objects, we're seeing them as they were in the past. This time machine capability allows astronomers to study the early universe, albeit indirectly. Powerful telescopes like the Hubble Space Telescope and the James Webb Space Telescope have captured breathtaking images of distant galaxies, some so far away that their light has been traveling towards us for billions of years. These deep-field images provide snapshots of the universe in its infancy, revealing galaxies in various stages of formation and evolution. By studying these distant galaxies, astronomers have been able to piece together a timeline of the universe's evolution since the Big Bang. They've observed that galaxies in the early universe were smaller, more irregularly shaped, and undergoing intense periods of star formation compared to their counterparts in the present-day universe. The Big Bang Theory isn't based on a single piece of evidence. It's a robust scientific framework supported by a convergence of observations from a wide range of sources. Like threads woven together to create a tapestry, these pieces of evidence combine to tell a compelling story of the universe's origin and evolution. We have the cosmic microwave background radiation, the faint afterglow of the Big Bang, which provides a snapshot of the universe as it was just 380,000 years after the Big Bang. We have the redshift of distant galaxies, indicating that the universe is expanding, and Hubble's law, which describes the relationship between a galaxy's distance and its recession velocity. We also have the observed abundance of light elements, which matches the predictions of Big Bang nucleosynthesis, and the discovery of distant galaxies in various stages of formation and evolution, providing glimpses into the universe's infancy. Taken together, these pieces of evidence form a compelling case for the Big Bang Theory, making it the most widely accepted explanation for the origin and evolution of our universe. Picture this: the universe, smaller than an atom, a point of unimaginable heat and density. Then, bang! The Big Bang erupts, expanding space itself. Imagine a balloon with galaxies painted on its surface. As you inflate the balloon, the galaxies spread apart. The universe was a chaotic soup of energy and particles. Imagine a mosh pit of subatomic particles colliding at unimaginable speeds. As the universe expanded, it cooled, like a hot cup of coffee. This cooling allowed energy to convert into matter. Think of it like steam condensing into water droplets. Energy condensed into quarks, leptons, and bosons. It's hard to imagine our universe emerging from such extreme conditions. But like a master chef, the universe transformed chaos into order, energy into matter, and ultimately, into the cosmos we know today. As the universe continued to expand and cool, the cosmic soup of elementary particles began to settle down. Imagine a dance floor after a wild party, the lights dimmed, the music fading, and the dancers slowly pairing up. In a similar way, quarks, the introverted wallflowers of the particle world, began to clump together, forming protons and neutrons, the building blocks of atomic nuclei. But the universe was still too hot for atoms as we know them to form. Electrons, like restless partygoers, zipped around, constantly colliding with protons and photons, preventing them from settling down into stable orbits. The universe was a glowing fog, opaque to light, a cosmic pea soup you couldn't see through. However, the universe's expansion and cooling continued relentlessly. After about 380,000 years, the temperature dropped to a critical threshold, about 3,000 degrees Celsius. At this temperature, electrons, finally ready to slow down, could be captured by the positively charged protons, forming the first neutral hydrogen atoms. This event, known as recombination, marked a profound transition in the universe's history. Imagine the universe suddenly switching from a dense fog to crystal-clear clarity. With electrons no longer scattering photons, the universe became transparent to light. The photons, previously trapped in the cosmic soup, were free to stream across the universe, carrying with them a faint afterglow of the Big Bang, a whisper from the early universe that we detect today as the cosmic microwave background radiation. After recombination, the universe entered a period known as the Cosmic Dark Ages. With no stars yet formed, the universe was a vast expanse of mostly neutral hydrogen and helium gas, bathed in the fading glow of the Big Bang. Imagine a dark, quiet room waiting for the lights to come on. But this darkness wouldn't last forever. Hidden within this cosmic darkness were the seeds of a future filled with light. Gravity, the universe's master sculptor, began to exert its influence on the slightly denser regions of gas, pulling matter together into clumps. These clumps over millions of years grew denser and hotter, eventually reaching temperatures and pressures high enough to ignite nuclear fusion in their cores. Thus, the first stars were born. These first stars were unlike any we see today. Composed almost entirely of hydrogen and helium, they were massive, hot, and short-lived, burning brightly for a few million years before exploding as supernovae, seeding the surrounding space with the heavier elements forged in their nuclear furnaces. These stellar explosions marked the end of the cosmic dark ages, and ushered in a new era of cosmic evolution. Imagine the universe suddenly illuminated by countless brilliant stars, their light piercing the darkness, their energy transforming the surrounding gas. These first stars were the pioneers of the cosmos, setting the stage for the formation of galaxies, planets, and ultimately, life itself. Section 4. The Ever-Evolving Cosmos. A Universe in Motion. The story of the universe doesn't end with the formation of the first stars. It's a story of continuous change, evolution, and transformation. A grand cosmic dance that's been going on for nearly 14 billion years. The universe is not static. It's a dynamic, ever-changing entity constantly expanding, evolving, and surprising us with its wonders. Driven by gravity, the first stars clumped together to form galaxies, vast islands of stars, gas, and dust. Within these galaxies, new generations of stars were born, lived out their lives, and died, enriching the interstellar medium with heavier elements, setting the stage for the formation of planets, and ultimately, life. Our own Milky Way galaxy, a spiral galaxy containing hundreds of billions of stars, is just one of trillions of galaxies in the observable universe. And the universe is still expanding, carrying these galaxies further apart, stretching the very fabric of space-time. The universe's story is far from over. New discoveries are constantly being made, challenging our understanding of the cosmos and raising new questions. From the mysteries of dark matter and dark energy to the search for life beyond Earth, the universe continues to beckon us, inviting us to explore its wonders and unravel its secrets. A Universe of Wonder, reflecting on the Big Bang's legacy. The Big Bang Theory stands as one of humanity's greatest intellectual achievements. It's a testament to our curiosity and drive to understand the universe. From a tiny point to the vast cosmos, the Big Bang Theory is awe-inspiring. It challenges our perceptions and leaves us humbled by the universe's grandeur. Imagine our ancestors, filled with questions about the stars and existence. Today, we've pieced together a remarkable understanding of the universe's history. The Big Bang Theory is a profound paradigm shift in our understanding of the cosmos. It tells us that the universe is dynamic and evolving. It's a dynamic, evolving entity with a beginning, a history, and perhaps an end. It tells us that we are part of this grand cosmic narrative, connected to the farthest reaches of the universe by the echoes of the Big Bang. This realization fills us with a sense of wonder and awe, reminding us that we are part of something much larger than ourselves. It inspires us to ask deeper questions, to explore the unknown, and to push the boundaries of our knowledge. The Big Bang Theory, far from providing all the answers, opens up a universe of possibilities, inviting us to embark on a journey of cosmic discovery. The Big Bang Theory isn't just about distant galaxies, exploding stars, and the fabric of space-time. It's also a story about us. The very atoms that make up our bodies, the air we breathe, the earth beneath our feet, all were forged in the fiery crucible of the Big Bang. We are, in a very real sense, children of the cosmos, made from the ashes of stellar explosions. Imagine the journey of a single carbon atom, from its creation in the heart of a dying star, to its incorporation into a molecule of DNA, to its role in the complex symphony of life. It's a journey that spans billions of years and connects us to the vast cosmic web of matter and energy. The realization that we are stardust, that we are intimately connected to the cosmos, has profound implications. It underscores our place in the universe, not as isolated observers, but as active participants in the grand cosmic drama. It reminds us that we are part of a vast and interconnected web of life, sharing a common origin story with every living thing on Earth. This understanding fosters a sense of humility and interconnectedness, reminding us that we are but one species on one planet, orbiting one star, in one galaxy among trillions. It compels us to cherish our pale blue dot, the only home we know, and to protect the delicate balance of life that makes our planet so special. The Big Bang Theory isn't just about distant galaxies, exploding stars, and the fabric of space-time. It's also a story about us. The very atoms that make up our bodies, the air we breathe, the earth beneath our feet, all were forged in the fiery crucible of the Big Bang. We are in a very real sense children of the cosmos, made from the ashes of stellar explosions. Imagine the journey of a single carbon atom from its creation in the heart of a dying star, to its incorporation into a molecule of DNA, to its role in the complex symphony of life. It's a journey that spans billions of years and connects us to the vast cosmic web of matter and energy. The realization that we are stardust, that we are intimately connected to the cosmos, has profound implications. It underscores our place in the universe not as isolated observers, but as active participants in the grand cosmic drama. It reminds us that we are part of a vast and interconnected web of life, sharing a common origin story with every living thing on Earth. This understanding fosters a sense of humility and interconnectedness, reminding us that we are but one species on one planet, orbiting one star, in one galaxy among trillions. It compels us to cherish our pale blue dot, the only home we know, and to protect the delicate balance of life that makes our planet so special. The Big Bang Theory isn't just about distant galaxies, exploding stars, and the fabric of space-time. It's also a story about us. The very atoms that make up our bodies, the air we breathe, the earth beneath our feet, all were forged in the fiery crucible of the Big Bang. We are in a very real sense children of the cosmos, made from the ashes of stellar explosions. Imagine the journey of a single carbon atom from its creation in the heart of a dying star, to its incorporation into a molecule of DNA, to its role in the complex symphony of life. It's a journey that spans billions of years and connects us to the vast cosmic web of matter and energy. The realization that we are stardust, that we are intimately connected to the cosmos, has profound implications. It underscores our place in the universe not as isolated observers, but as active participants in the grand cosmic drama. It reminds us that we are part of a vast and interconnected web of life, sharing a common origin story with every living thing on Earth. This understanding fosters a sense of humility and interconnectedness, reminding us that we are but one species on one planet, orbiting one star, in one galaxy among trillions. It compels us to cherish our pale blue dot, the only home we know, and to protect the delicate balance of life that makes our planet so special. The Big Bang Theory isn't just about distant galaxies, exploding stars, and the fabric of space-time. It's also a story about us, the very atoms that make up our bodies, the air we breathe. Unanswered questions, mysteries yet to be solved. The Big Bang Theory, while remarkably successful in explaining many aspects of the universe, is not without its mysteries. Like a detective novel with a few missing pages, it leaves us with tantalizing clues and unanswered questions, beckoning us to delve deeper into the unknown. What caused the Big Bang itself? What existed before the singularity? What is the nature of dark matter and dark energy, the mysterious substances that make up the vast majority of the universe's mass and energy budget? These are just a few of the questions that keep cosmologists awake at night, driving them to develop new theories, build more powerful telescopes, and explore the universe with ever-increasing precision. The search for answers to these questions is a testament to the scientific method's power and limitations. It's a reminder that science is not a collection of static facts, but an ongoing process of discovery, a journey of exploration where every answer often leads to more questions. The mysteries surrounding the Big Bang are not cause for despair, but rather a source of inspiration. They remind us that the universe is far stranger and more wondrous than we can imagine, full of surprises waiting to be uncovered. They challenge us to expand our understanding, to push the boundaries of human knowledge, and to embrace the unknown with a sense of awe and anticipation. A universe of possibilities, the future of the cosmos. The Big Bang Theory marks the beginning of an incredible journey of cosmic exploration. We can expect more surprises, challenges, and awe-inspiring discoveries. New telescopes will peer deeper into the cosmos, capturing the universe's first light. Advances in particle physics will unravel the mysteries of the early universe. The search for life beyond Earth will continue with renewed vigor. The possibilities for discovering life are vast and tantalizing. The Big Bang Theory has revolutionized our understanding of the universe. It's a story that invites us to explore the cosmos and embrace infinite possibilities. The universe will never cease to inspire us.